Hello and welcome back to ST118 Statistics and Applications, Session 5. In this session, or this series of videos, I'd like to discuss about this interesting topic that is seldom discussed, seldom emphasized, and sometimes or quite often even outright forgot to be discussed, not even in the syllabus. All right. So what's this mysterious subject in statistics that is having this importance and yet uh, forgotten attention? And that is called the non-parametric hypothesis test. Right. So that is the main topic that I want to talk about. Parametric hypothesis tests. And this is a whole series of tests that are having this non-parametric um, feature, right, or lack of assumptions, basically. And these tests, they have sort of a sibling, right, or brother or sister test that we have seen, and that's the one population, two population mean, three population, three or more population means test. Right, so we have seen them, and those tests discussed in the earlier videos, they were introduced as uh, the usual textbook tests, and actually they are parametric tests. So what's this about? What is parametric and non-parametric? So something we will talk briefly about. And in this particular video, I want to talk about the common advantages, benefits that you would get when you use them. All right, so I just want to talk about all non-parametric tests, share these advantages and benefits, and also I like to discuss about application areas as usual, right? And partly also uh, why parametric, right? So where parametric tests fail. Okay, essentially. All right. So in this video, we won't go into the details of the specifics of one population, two population, three population uh, means test, the equivalent versions in non-parametric tests. But I want to just talk about the nature or the contrast between parametric tests and non-parametric tests, right? Uh, and then in subsequent videos, we can go further into the details and the specific calculations and examples involving each of them. Okay, so now what is parametric, right? So let's begin by asking ourselves, what is parametric? What is non-parametric, since this is our subject today, right? As opposed to parametric. Non-parametric means there is no parameter. Remember what's parameter? Parameter is the population parameter. Population parameter. So the non part refers to the lack of or the removal of assumption of parameters. So what are parameters? The population values, right? So population mean, in hypothesis test, we need to have a hypothesized value, we need to assume that the normal distribution follows normal distribution and has certain mean and certain standard deviation, right? And if it is lacking in the knowledge of standard deviation, we use t distribution. We try to cope with it and still in a parametric way, right? Assumption. So assumption of parameters, distributions, and various other assumptions and variances. The lack of assumption is a very liberating benefit already. So already you can tell the lack of it means we relieve ourselves from having to assume this, assume it is normal, assume the variances are equal, right? Remember all the discussions there? Assume that in hypothesis test, we assume that the population mean, mu, all the while follows our hypothesized mean 5, right? So we need to make those assumptions throughout our tests. We have gone through those discussions, and basically the logic is sound, provided you can make those assumptions. So typically in classrooms, we will, and I'm part of the culprits, part of the propaganda saying that we'll wave our hand and say that, okay, assume that the data we are testing is normally distributed, right now. So we just make those assumptions. Or the exercise questions or exam questions will make those assumptions for us so that we can then legitimately carry out the Z test, T test, and even for chi-square test, F test, they also require the parent distribution. That means the data that we are measuring to be following normal or close to normal, right? So in real life, is there normality? Point is, in real life, IRL, right? Not LOL, but IRL. In real life, normal distribution, right? Normal distribution is strictly not found. Sorry to say this, strictly not found, because a perfect normal, any normal distribution will stretch from minus infinity to infinity, right? Yeah. So normal distribution will imply from minus infinity to infinity. But we never have such a thing in real life. You can have very rich person having billions and millions of dollars, but that's hardly infinity in a mathematical sense. Right? But this is mathematical sense. So there's a big how should I put it, gap, right, between assuming $500 billion worth is equal to or can be replaced by infinity. And that's very stretching to make that kind of assumption or that kind of equivalence, right? So end up what happens? Well, our calculations will still go through, but we'll get some numbers, whether it is p-value or it is probability or it is test statistic. In the end, the number itself might be having a lot of errors embedded, and we hardly know because we're just following the so-called orthodox way of doing things with no other comparative methods or results to compare with, right? So in real life, normal distribution is not found at all. And so we are always approximating. We are always assuming, right? Assuming without proof, we just assert, right? Approximating, sort of like if it is somewhat lumpy kind of distribution, just like a mole, right? A mound, we will just assume it is normal. But the tail is finite, right? Tail starts from say 1 to 10, but we assume it is from minus infinity to infinity. And that's very, very strange, right? And very, very absurd if I were to tell you to assume 1 is minus infinity, 10 is infinity. I mean, that's very hard to understand, very hard to teach, very hard to convey that notion. So, so why is it that in textbooks, I assume a lot of you audiences here, students by and large, right? You will find that your syllabus doesn't even talk about this because it's kind of legacy, right? Started off with the focus on philosophy, mathematics, right, and theoretical statistics, right? Even though statistics is mainly applications, the most application-oriented part of mathematics. So mathematics, there are two branches: pure mathematics, applied math. Applied math deals with touching reality. So calculus, integration, differentiation, optimization, statistics. And statistics is the most touching reality part of applied mathematics. And even so, there is still a big component of theoretical statistics involved. And historically, that part is emphasized a lot because, as I kind of briefly introduced earlier on, it's easier to talk about the sort of mathematical realm when in the earlier development of educational history and society, it is probably harder to gather application areas. Right? Information has more resistance to be transmitted. It's not as efficient as today. There wasn't YouTube then, right? So it's more illustrative and easier to teach in formal settings like classrooms and institutions. So that started back then, which was reasonable, perhaps, and it got carried down right all the way to modern days, and that's one, right? So legacy passing of the structure, and so syllabus hardly changed from then till now. But that's also reinforced by the technological development. So back then means maybe in the 1800s, right? So back then, no calculators, right? So no computers, no Excel, no R, no Python. So tough. So calculating p-value is just like maybe the hardest exam problem. Whereas today we just run a button, call a function, and then the number will come out, no matter how complicated the p-value calculation is. So lack of access to technology, calculators, and all that, no ZAC table, right, in the very, very early days, leads to a lot more focus on assumption, right? Assumption of somewhat easier yet still useful mathematical constructs, such as normal distribution, such as t distribution, right? So they are by no means simple, easy, like 1 plus 1. They are still complicated mathematical objects. Still, it was painstakingly constructed to mimic real life, right? So it's very perfect in the mathematical world. Normal distribution, t distributions, they are perfectly symmetrical, right? Perfectly zero skewed. Now, when I put in the word perfectly, because it is true, right? And yet it brings out the very ironical aspect of it all, and which is that in real world, you could hardly find anything that's perfect. It's just messy and chaotic and not symmetrical. Right? So that is the so-called problem, and basically what you have observed, right? So you've been learning parametric methods, and you do have a rich source of textbooks, exercises, and whatnot. But non-parametric methods are very useful. So here I'm going to do a bit of salesman talk to sell you the advantages, right? So let's talk about the advantages. In using a non-parametric hypothesis test. So this advantage and benefits, it's not that you are using hypothesis test. It is in using, applying non-parametric methods in general. So this means all these advantages and benefits, they apply equally across all the non-parametric hypothesis tests for 1 population, 2 population, 3 population tests. And what are they, right? So first thing first, I like to note that your conclusions are more defensible. Okay, your conclusions are going to be more defensible. How come? I'm going to say that you will uh, you will invite lesser challenges and suspicions, right, about your conclusion, right, and more because you make less assumptions. Simply, just due to the fact that you make even one lesser assumptions, and furthermore, non-parametric methods make a few lesser assumptions, and these assumptions are not trivial assumptions. They are very core assumptions that make parametric methods work, right? So you're not making them. Um, so that's why your conclusion is less susceptible to attacks, such as you said we should reject H naught by making assumption that the test scores are normally distributed. But look, test scores are not really normally distributed. They're not symmetrical, right? And then we have a problem, right? That oh well, because you also learn, you try to wave your hand just like how you learn in classrooms, right? But by always assuming without asking why. And yes, when you do that in real life, and when promotions are at stake, when convincing customers are at stake, right? Completing the sales, they are at stake. Then yes, you will be inviting challengers, right, to all the assumptions that you are making, but you're not when you're using non-parametric methods. Uh, no need, right, to assume idealistic uh, normal distribution of the data. Yeah. So by that's just one of the tip of the iceberg, right? That's the key liberating factor. You don't need to make this unrealistic assumption. So thereby making your calculations, your conclusions much more defensible. First of all, it doesn't invite people to ask, "Are you sure?" Right? Okay. So next, I would like to propose that non-parametric methods, they are very robust. Robust against what? Robust against so-called non-cooperating data, and you will see that a lot in real life. Okay, so non-cooperating data is found almost all the time in all measurements in all survey. They would be, for example, non-cooperating data. What are they? Example, outliers. Outliers, if they happen persistently, could be news, could be a signal for new discovery, but oftentimes it's otherwise. It's like, oops, my hand shivered. Oops, my instrument wasn't calibrated. Phew, so it went off the chart, but it was recorded. So what should you do? Is that considered one sampling of anomaly, and you want to delete it? So it's like kind of a problematic, right? So you don't have outliers. You don't you don't have to um, assume that skewed distributions are symmetrical. They are basically not symmetrical. You will face a lot of skewed distributions in real life. I'll spend a little bit of time giving some examples in a while, right? So in real life, skewed distributions, they are plenty. It's the opposite. Normal distribution is hardly found. Did I say something there? Yeah, okay. Normal distribution is hardly found. So normal distribution is really abnormal. And abnormal distributions, if I may say, skewed distributions are abnormal. They are the norm, right? They are the norm. You also have data that gives you varying variances that change, right? And if you talk about ANOVA, such as ANOVA 3 population means test or more, you have knowledge of the fact that the different populations that are participating in the ANOVA test, they have different variances, right? Because of contextual expertise. Like if you are a teacher, then you teach full-time students, young students, versus nighttime working adult, part-time students, nighttime. All right, so they're already so tired. They have work, they have boss, they have family, and they still attend class. Very strong spirits. However, the the variance of the test scores likely will be higher, right? Just based on this description of the participants, the students, you can tell because they come from all walks of life, right? Some will be working night shift, some might be executives, some might be production supervisor, whatnot. So they come from all walks of life, and then you expect all have consistent scoring ability. So I mean that's strange. Full-time students, fine. There are also differences, but they are trained as a batch, right? Like classroom style. So class by class. So more or less is made to be more consistent. They are sort of strictly trained by the same teacher, and so they perform well, or very loosely trained by the teacher, so they together not perform well, and the variation amongst themselves will be lesser. So the differing variances will lead to some breakage of assumption. Also, if you're using parametric tests, if you recall the two population means test, right, there's a need to assume equal variance in a particular branch. And for ANOVA, there's a need to always assume all population variances are the same. Also, so this in real life is the norm, and yet our only tool and weapon is to assume the norm doesn't exist. Very strange, right? So that's the reason why we again need to revisit our toolbox, right? Anomalies in data, various anomalies, absence of data, and misbehaving data. And so this means that non-parametric methods, I want to put NP, but NP does mean different things. So non-parametric methods are very robust, right? Great to deal with messy real world readings or measurements. Okay, so that's another big reasons why we should consider. So I'm like a salesman, but I think to me I'm a sold person, right? So I think this is important. It is also assumption light. So it is robust because it is assumption light. That means it makes very little assumptions. Assumption light, right? So very few assumptions. So it's very robust. It's like the simpler the design, the more robust it will last, right? The more robust against the environment, rough usage, it will behave. So you can use it in different situations, in different sets of data, in different captured from different environments, in variety of settings, and still the methods, the non-parametric methods, will stand because it doesn't assume much. That means it's very hard to break, right? Very hard to break. In some textbooks that do discuss non-parametric methods, it is also described as distribution-free methods. In other words, there's no assumption of distribution, such as normal distribution. Assuming that the parent distribution, the set of data that we are measuring, assuming it is normally distributed, but we don't know the sigma, the population standard deviation. So in our test, we use the t-test statistic. Right? So that was the common narration in the parametric test. But in non-parametric settings, the whole procedure doesn't involve any of such assumption. So Oh, good, right? So more robust. And another point, seems like a lot of good points, right? So another point I like to bring up is the flexibility. Flexibility with the flexibility of non-parametric methods with variety of types of data types. So what this means is not just the measurement source. For example, I'm measuring the test scores, I'm measuring uh, what is it, the height, the weight. Not only that, but I'm also talking about the uh, ability to deal with ordinal, able to cope with ordinal data. Ordinal data, right? Ranks basically will be first, second, third, fourth, fifth, right? Yeah. So like in Olympics, gold medal, silver medal, bronze medal, right? So the ranking basically is one, two, and three. And one, two, and three doesn't mean that they are, if you're talking about running, they are 10 seconds apart. They are 5 seconds apart. No, right? The first could be 50 seconds. The second, the run up, the first run up could be 90 seconds, right? Like way after. Although in Olympics, that may not be that drastic difference, but you know what I'm trying to say. They are non-proportionate. First, second, third, the intervals are not linear, are not constant even. So you can have ranks. You can have one, two, three. You can have even qualitative data. Qualitative data. Okay. For example, number of passengers, buying tickets for economy class, business class, and first class, right? So we know first class is first class, more first than business class, and business class is more first than economy class. But the ticket prices, they are different, are very, very different. It's not times two or times three, right? So sometimes times 10. So again, parametric methods will require some sort of proportionality in most cases to make sense of the data. But and then even in qualitative case, parametric methods, bye bye, right? There's no normality in qualitative data. Then we are done with. So problematic. Um, that is really a very different and yet another benefit, right? Am I done? Give me just one more dot, right? So one more dot here, very important. That initially might sound like a mathematical benefit, but actually it is a business benefit, and that is okay with small sample size. Remember our discussion with parametric methods that if sample size is our hard work, right? Sample size small, do little work. Sample size large, do more work. And because of the parametric settings, assumptions, we needed CLT, CLT to say that, in real life, most parent distributions, again, the distribution of the data that we are measuring, typically they are not normal. So non-normal parent distributions, never mind, do hard work. Central limit theorem comes in to say that don't worry, your sampling distribution of sample mean will be normally distributed. So we're very keen on making things normal just because normal distribution was maybe one of the first things that were studied and very familiar with many mathematicians, statisticians, teachers, professors, and that's how it gets propagated to the to such an extreme that now even things that are quite obviously not normal, we will try to make it normal, right? We will try to deploy central limit theorem and all that. So that is not to say that all the statistics are wrong, but rather in the light of a viable competitor like non-parametric methods, maybe you should consider, right? So what's this? What business advantage has this got? Uh, so we first describe a little bit of the obvious. We don't need CLT. We don't need central limit theorem like in parametric methods to save us. We can, or rather, the non-parametric test methods can directly deal with small sample sizes. Very comfortable. All right. In fact, it's the other way around. That when sample size get large, then the computations, the native direct computations that deal with um, ordered statistics, right? So in the calculations of ranks and all the test statistics and p-values in non-parametric ways, they get so complicated. They get combinatorically explosive, like various combinations, permutations involved. It gets so large, right? So when n is large, when you do more work, computer gets even more work to do, exponentially bigger, more work to do, and then we will find means to approximate the calculations, like using normal distributions, using other distributions, chi-square distributions, to facilitate the computation, the speedy computation of test statistic, p-values, and all that stuff. Right. So, and a lot of times the what you call that, the test the critical values. We need critical values, right, involved in hypothesis tests. The critical values for a lot of these tests, they were pre-computed using simulation, multi-color methods, numerical approximations, using normal or chi-square or other, reasonably derived mathematical approximations to simplify the calculations so that the table can be quickly calculated and not take a lot of time. So it's like the earlier days of doing normal distribution, right? Earlier days, we didn't have calculator, Excel computers. So it was like by hand. So so long as someone has calculated the test statistics, or rather the critical values, put it in the table and share with everyone. Right? So now we are like doing that. Even with computers, it will take a long time. So no need CLT, right? It's a tool that operates effectively. So non-parametric methods can directly, right, deal with small sample sizes. Right. And remember, so this is a business benefit because n small implies the cost of data is lower. Yeah. If you think about interviewing 10 households compared with interviewing 1,000 households, you can already imagine the tiredness. Don't even talk about money, the time that you need to spend right now. Yeah. And of course, versus parametric ways, we tend to encourage larger sample size, right? So it just means more expensively, right? So you need to gather more data. And this will also come in many situations as a limiting constraint. So in parametric methods, we need to have, or we are encouraged to do more hard work, to touch reality more, to know the reality more, so as to get a more stable, reliable outcome in computation. Right? But even if you can afford the money, you may not have that sample, or you may not have the sample in time for you to finish your experiment. So, such as clinical trial, if you're an economist studying economic disasters, financial meltdowns, your interest is different from others, right? People want the stock market to go up, you want it to crash, to study the effects. That's good because we need people to study the effects, but your sample size is really hard to come by, right? It's like 10-year one time or 8-year one time. So rather hard to come by, even if you can afford the money, but you cannot get it. But as we know, theoretically, if you wait till infinity, you will get many, many, right? So that's the problem. That's the issue. So these 4 points are each of them is already a very big attractive factor against the parametric methods. So much less to say that we have 4 big points, right, to basically uh, compete against the parametric methods. Yeah. Okay, so let us switch gear a little bit to now talk about some situations, okay, the application areas. I have a little bit of a space below, so I want to see if I can salvage that. So let me see. Okay. Over here. Okay. Very expensive real estate on the screen. All right. First thing first is to sort of quickly give some idea about um, some examples, some ideas about uh, application areas. So still, we are using the non-parametric methods to determine population mean, but because it's non-parametric, we won't do mean. We'll do median instead. All right. So non-parametric methods, they typically involve population median, right? So it becomes one population median test rather than mean test. Two population medians test. Three population or three or more population medians test. So nevertheless, the results are still very useful, very robust, because, for example, we typically hear of uh, income distributions being very skewed, right? Being lopsided. So the average will be high because the rich will probably take up 1%, 2% of the population, but they are super, super rich, right? They're disproportionately rich. So much so that they average up everyone's annual income. So it seems like the annual income of that country or that city is very high. So typically, we don't use mean to describe a city or a country's income, but rather we use median, right? And you probably have seen that around if you just browse around the internet space to look for country, GDP or else personal income, right? Of listed by countries, you will find that typically the median income is being given. Okay, so we want to just give some examples. What are the examples? First, I like to highlight non-normal situations. Okay, so non-normal situations, non-normal measurements, right? And that actually covers the world. So it's actually covering the whole world. All the measurements are basically non-normal. But to illustrate, let's just talk about uh, medical recovery time as an example. Or patient ward time. All right. Uh, most of it will be 1 day, or if you include inpatient, right? So 0 day, 1 day, 2 days, right? So 3 days, 4 days, lesser, right? And 10 days stay. Even if your friend tells you, I just get discharged from hospital. After 10 days stay, you're like, wow, so long, right? 30 days stays, right? And there are people who stay there for 90 days, right, before finally getting discharged, right? So it will be a bit like income, it's rare, but not impossible for patient to stay there for 3 months, even 1 year, right? Something like that. Okay, so that's the medical recovery times. We can talk about what is it? The salary distribution, right? Just like income, salary distribution will be more visible if you are the HR manager or director, whether in small or big companies or MNC, right? You will see salary distribution because there's always one CEO by construction. We won't construct a pool of 10 CEOs to fight against each other. So by design, there'll be one very, very highly paid CEO, always highest paid CEO. Very strange, right? Highest, not strange, but strange in the construction. Um, so, and then the deputy CEO, right? The directors, the mid managers, and all the way down. And all the way down also means salary all the way down, right? So by construction, there'll be a lot of people at the left end, and the right tail will be very thin and sometimes long, right? So that's the salary distribution. We can talk about stock returns per dollar investment, right? And typically is known to be having fat tail or heavy tail. Heavy tailed distribution. Heavy tail distribution means heavy tail, right, on the right end. Typically, stocks don't return. Okay, fine. Typical stocks return mediocre returns, right, and even lose money, negative returns. Fine. Uh, you do have stocks that, especially in the rising market, right, economic boom times, you do have stocks that have very good chance of getting very high return, right, with high probability, and that's why that we call that the fat tail, or another word for that is called the leptocurtic. Just another word for you to boast about. Okay, so that's another example of not being normally distributed. That's another example. And we can also talk about other things, right? I'm just going to list them. Revenues, assets, right? Number of employees, sales volume by product, and so on. A lot. Almost all measurements are non-normal, so that's why it's very easy to draw that. Okay. Next we have ordinal data situations, non-interval scales like discrete values. They are numbers, but they are discrete, and they may not be proportionate. It may be 1, 5, 15, 30, something like that. So it may fitting into the context, it is reasonable, but for example, I think volume, right? Volume is to our ears, what is loud is not proportionate. Right? So when it's very silent situation, a bit of sound is already considered doubling the volume. So typically, you see those amplifiers with volume control, they go by decibels, right? So that's more like a non-linear scale. So you have these kind of very natural occurrences, and also rankings, right? We talked about that. Rankings are very common, right? And NTU just went up in ranking, right? So that's after summarizing all the measurements, they summarize the summaries further, right, into a rank so that people can quickly talk about that or have a meeting and say this is not good enough, right? We should do better, right? So many examples circling around these. I probably give a few to just enlighten your thinking cap. But customer satisfaction survey, maybe a little bit squeezy, but you get the idea. Um, Employee performance. Sometimes we just give them ticks. So is this employee performing with excellence, right? So 5 star, uh, quite good, right? 4 star, right? Satisfactory, 3 star, could be having improvements, so 2 star and something like that. So employee performance, but actual measurement could be differing by a lot and also not quantifiable, right? So maybe excellent performance could be that the person completed two very complex, long running projects, so not easy. Two will be very good already, super already, right? Another person completed five, what in most managers' opinions could be like moderate challenge difficulty. So even if you complete five projects, it's just maybe 4 star, not 5 star, right? So we get uh, these situations very frequently in real life. So uh, that's why we again have such, you know, situations. Then you forcefully use parametric methods, assume continuous scale. It's going to make things even worse, right? Okay. So we also have other things like credit ratings, right? Credit ratings, personal credit ratings, company credit ratings, bond sales credit ratings, right? And so on. Risk categories, risk categorization for companies, for individuals, right? For people borrowing money from bank will categorize them into very risky, don't lend money, right? Moderately risky, higher interest rate, or something like that, right? Uh, Educational level, and obviously that's very prevalent. Everyone knows this, right? Educational level, we don't have one, two, three, four, five. Not proportionately. We can say primary school is one, level one, right? So secondary school, high school, level two. We can say that, but we know that the difference, right, between primary school and secondary school and junior college or pre-college and university, very big gap, right? Not the same gap. Right? All these things, right? I think you can list down even more. Uh, then we have other situations like uh, small sample size, small sample size, and or heteroscedastic. That means changing variance or differing variance. So in a small sample size, we know, right? In other situations, we have multiple populations, like ANOVA, right? We are trying to test three populations, three groups of measurements. Um, by necessity of ANOVA's method, we have to assume that these three groups, for example, temp staff, contract staff, permanent staff, their happiness level have similar or equal variance. That's strange, right? You're just saying from thin air that they have equal variance. Why should they have equal variance, right? Permanent staff, they are always there in office. Why should they differ? Why should their variance be different from why should their variance be the same as the variance of contract staff, who is like on and off, temp staff, on off, right? So there's no good reason to make this assumption. Very, in a way, ridiculous to make this assumption without proof, just saying, just assuming, right now. Yeah. So in this case, then we want to consider non-parametric methods. What are the real life situations? Uh, Rare disease or cancer cases, participation for new drugs, right? Right. So these are rare to come by, even if you have a lot of money. Uh, you may not get the voluntary consent, right, in time to complete your clinical trial or whatever it is. Then you may have uh, stock price volatility. Okay, so stock price or share price volatility by industry, for example, right? The volatility, the variability of stock prices in the banking or financial sector should not be expected to be the same as manufacturing sector, right? Because manufacturing sector by construction, by operational design, is supposed to be stable. From quarter to quarter should be as stable as possible, right? The managers are hired to make it stable, having maintaining the demand or else increasing the production. Whereas banking stocks and all this, they are subject to various economic factors and influences and economic, political, geopolitical influences. So why should you assume that the variances are the same, right? So again, very hard to come by. Okay, good. So essentially, these are the sort of like touch the ground where the tire meets the ground situations, broad situations. And I try to give some concrete examples that you probably have come by, have heard of, so as to be able to associate that it is very prevalent, right? It is very common to see and observe situations where non-parametric methods are much more applicable than parametric methods. Okay, next, I'd like to give a bit more direct discussion about distributions, because this is very central to the assumption of parametric methods. Distribution situations from real life measurements. Okay. Three categories that I want to go into, right? Number one is highly skewed, not skilled, not SKILL, but skewed, highly skewed distributions. Okay, so highly skewed distributions, they appear as I'm just going to give brief ones. Yep. So they appear as income and wealth. Income is the cash flow, wealth is the accumulated assets. Right. So income, wealth, typically you have what do we have? Income and wealth, typically we have this kind of situation, right? In maybe developed countries, few people get $0. Then most people are here. Then you have some people getting very high income, something like that. Of course, in undeveloped, less developed, less socially oriented countries, maybe you have this. Quite a lot of people getting $0, right? Something like that. And then a fat tail, maybe. Okay, whatever it is. So it can change, but however it changes, it's not going to look like normal distribution simply because there's no one getting negative dollars. Okay, we're not considering that as negative, huh? Just the pure income. Okay, so next we can talk about time to failure. So very, very different. Time to failure of any machine. Right, time to failure of any machine. How does it go? Well, typically you imagine the air conditioner, right, or bicycle. So it will operate until some average time. Uh, Most of the bicycles will, let's say not bicycles, air conditioner, right? So air conditioners. So maybe they don't break down in the first month, but most of them will break down after 3 years, right? Something like that. And then 4 years, 5 years, 6 years, and then tapering off. So there may be two steps or something like that, or gradual descent, and that will be very product specific. But it may not start from zero. It may also have a mid-air jump. That means not gradually more and more as time passes, but rather suddenly 10%, 12% will start failing. So it all depends on the product and the nature. But again, you see that it's not normal. Next is hospital stay, and for that matter, maybe hotel stay as well. So it applies to patients and tourists stay duration. You can see that typically, okay, for tourists, you won't come to a country and stay 0 day, right? You will have some 2 to 3 days, maybe 4 to 5 days. So 2 to 3 days a lot, 4 to 5 days lesser. Some people stay for 2 weeks, some people stay for 3 months in hotel, right? And most of them will not stay 0 days. Hospital, so same thing, right? If you're hospitalized, you may stay for 1 day or more. So same thing. But of course, it is possible that if you include transit passengers, because they also spend some money. So you are Singapore Tourism Board, right? You also include transit passengers who spend money. So they don't stay any day, so they consider 0 day. So transit, a lot of passengers, so like that. So then it'll be like this, isn't it? Yeah. So the shape changes. Again, you don't call that normal distribution, do you? Okay, so that would be our example. Now you notice that these are mostly right skewed. Agree? Yeah, they are right skewed because the tail is longer on the plus infinity end. So it's called right, and it's on our right side as well. But it's also called positively skewed because the tail is pointing towards infinity. We said the tail because it is obvious that there is this tail. We hardly will call the left side a fat tail, correct or not? Yeah. So one look and we will say there's a tail on the right side, so right skewed or positively skewed. And we can also come up with a few examples. It's a bit rarer, but a few examples of left skewed distribution that occur naturally, right? So for easy tests, what happens? For easy tests, most people will get 100 marks, right? So it's limited by the cutoff here, right? So 100 marks. Most people, so high proportion of people, maybe here like this, right? And few people will fail, even though there may be one or two doing bad, like this. Right? Or else, so it's a cutoff, right? Or else it will be, basically having another peak, a little bit slanted that means most people get A instead of A plus. Some very brilliant ones will get A plus. Then hardly anyone fails, but although there's some people who forgot to come, who forgot to prepare themselves, that. So in these cases, they are very obvious left tail, right? So easy test that tends to lead to such a case. Now, if that is just a test, then maybe it's very limited. We can talk about age at retirement. Whoever declares retirement, right, then we will capture that age. Now, let's think about that. How will the distribution look like? So many people, they declare retirement. Now, clearly that is going to be hard limited by the lifespan of people. Let's say that's 100 also right now. So we can say that 70, right? So some people, they retire at 55, 60, 65, 70, and then 100. So most people retire at, let's say 60 to 70, like this. Some people as early as 55, then dropping off. Then a few successful entrepreneurs, young entrepreneurs, right? They retire at 20 or 30, and yeah, and then like that, and then you're forced to retire because your age, your lifespan is up, right? So, but yeah. That would again be a very obvious left tail stuff, right? Another one could be like a Likert scale, customer satisfaction rating, right? We talked about that, and for that matter, it can be any feedback. Also, teachers' feedback, right? Feedback from me, and any feedback in highly rated, highly, not just any situations, but highly rated or well regarded settings. So, for example, a Michelin 5-star restaurant, something like that. So you do customer service. So what happens? It's already a legit 5-star Michelin restaurant. So out of the desire to obtain self glorification, right? So the chef did a little electronic thing to say, okay, as you step out, click the smiley face. Right. So do you rate us 5, 4, 3, 2, 1? So what happens? Well, because it's 5-star, right? So most 5-star. So most people will feel that the services are very good. Then some people will be not non-perfectionists. So they will say, well, you are never my perfect, you will never get my perfect score. And then that's about it. Then there will be a few people who will rate 3. And there will be some very, very strange people who will say, nah, it's still very, very bad. I need to call the waiter 3 times for the waiter to come by. So one smiley. Yeah, okay, so not very impossible, isn't it? Very natural, yeah. So then you end up seeing a very left skewed, left oriented kind of curve. Okay. Um, one more perhaps is to talk about tiredness of Singaporeans, tiredness of Singapore workers, or for that matter, happiness for Swedish workers. What happens? Tiredness. Tiredness will be in terms of score, right? Converted to score 100. So most people in Singapore they work a lot, so very very tired, and it doesn't drop to 0 at 100. There's still some. Then relatively speaking, few people will feel tired, less tired. So most people feel very tired at the end of the week, let's say. Then the same curve might apply to Swedish workers, right? So they're always very happy. Most of them are very happy, but very few will feel unhappy, right? So, and now you can see why what is that? Left skewed distribution also occurs quite readily, and you don't really have to find with great difficulty right now. Yeah. Okay, so that's one. Another aspect of distributions from measurements I want to talk about is non-normal. I don't want to call it abnormal, but from measurements we know that they are non-normal, right? So that's the that's the setting that we have. Okay, so from our measurements, from the real life context or environment, we already know that it is non-normal. That's what we are saying here. Non-normal distributions. Um, this can include, for example, bimodal. Bimodal means like two almost equal peaks, right? Bimodal, U-shaped, sort of like a inverted normal distribution. Uniform distribution, clearly not normal, right? And these are continuous. Continuous. And what happens if it's discrete? Then definitely not normal. So discrete cases. Discrete cases with finite, okay, especially with finite and small finite range. And of course, you can think of the dice, right? 1, 2, 3, 4, 5, 6. That's discrete. Range is finite. It's 1 and 6, not going to infinity. And it's short, right? 1, 2, 3, 4, 5, 6. And so in this case, very, very non-norm. So you cannot try to approximate the distribution of a dice with normal distribution, assuming it's normal distribution. That's bizarre, right? Nobody can agree. Simply because people gamble, people play with dice, people understand dice. You to say that 3 and 4 appears much more frequently than 1 and 6, that's nonsense to many people, right? You don't even have to study statistics to disagree with that statement. Okay. So what are some real life examples to help us connect that non-normality with real life, right? Let's talk about, for example, reaction time. Okay, reaction time to respond. So, example in police, in military settings, in, for example, training of dogs, cats as a business, of course, swimming, between athletes, between the reaction time between hearing the starting signal, bum, right, or and the athlete or the swimmer actually started moving. All these you can use high speed video these days to micro analyze down to the sub millisecond level, no issue, very precisely. And we find that it will never, right, be the case that when when a person, or rather when the signal hits, right? So this is the reaction time in milliseconds, perhaps, right? So amongst many athletes, police, military officers, trainees, whoever, right? Whenever there's a signal, stimulus, boom, right now, yeah, the response cannot be zero time. Immediately you do it. Even for cats, which are known to be very quick in their response, and they will never get bitten by snakes, right? Because snakes are like lightning fast, cats are super lightning fast, faster than the snake can move its neck and teeth to sink them into the cat's flesh, right? So the cat is really very fast. So the faster it is, the closer to zero. But for humans, it will be a big gap, right? And then most people, the quicker responding people, will be nearer to here. Then there will be some slower responses. Then there will be some who are like very slow. What's happening, right? So you get this kind of curve. Absolutely non-normal. Right? Something we have seen earlier on, but this one is to stress the fact that the shape is very non-normal. What is non-normal? Non-normal means it's not symmetrical. It means skewed, right? So skewed distributions, definitely they are non-normal. Furthermore, the range of valid measurements, right? We know it cannot be negative, but then for response time, it almost always cannot be zero also. So there'll be a fixed gap between. It all depends on the subjects we are measuring. Test scores with finite test scores. So these come with finite floor and ceiling marks, cutoffs. Right. So you by design, by construction, you cannot get lower score than 0 mark. By design, all test scores are standardized to 100 marks. Some we standardize to 50 marks, right? Some we standardize to 10 marks. So like customer rating, so same thing, standardized to 5 marks. So in these cases, then you have a very easy test or very difficult tests. So very easy test we have seen, very easy test, a hard limit of 100, right? So many people will be scoring here. So you might even have a very steep cliff, just a very extreme illustration of easy tests over here, right? And then very difficult tests. So easy test, right? Difficult test, many people fail, right? So it can be here, many people 0 marks, right? Then some manage to score 1 or 2 marks, then like that, steep drop, and then maybe a gap, and then some coming alive here, 1 or 2. Dropping to 0, then coming alive. So this kind can happen too. I've seen them actually. Not in this sense, but I'm saying dropping to 0, then coming alive, right? Because that's by design, and your number of students is not really so huge that you can treat them as a real number line. Like 3.5 students also makes sense. Doesn't make sense in a class of 20 people, 10 people. 3.5 students doesn't make sense, right? In a class of 30,000 people, students in one class, right? Impossible in real life, but suppose that can happen, then 3.5, okay, you can kind of ignore that little bit of noise there, right? But it's just not possible in real life in most classes. Okay. What is also possible or interesting is that in a class setting, right? Sometimes we can see a particular test bringing out this aspect of students that behave like this. Right? Okay, so again, this is 100 marks. All right, we just standardize it, and a standard test, reasonable difficulty, it brings out this sort of almost equal peak here. And what does that mean? This is our bimodal distribution. So 2 peaks, 2 modes, right? 2 modes. And usually this is a blur, not by intention, but it reveals, right, a blur of 2 populations. So that means there are 2 subpopulations hidden within. Either the person capturing this score, the teacher, or maybe the institution, assign the students, or the students themselves elect. This happens with elective courses. All students, engineering, humanities, social sciences, natural sciences, medicine, whatnot, right? All will have some students being attracted to this elective course. Maybe this course is about generative AI. Okay, so everybody, from all different discipline registers. But once they register, some of them regret, right? So this bunch will regret because they thought the topic was interesting, but when they come in, it's all alphas and betas and theories and proving. So they are like, oh no, right? So the first test, flunk, right? So this is passing mark. The rest, they got what they were expecting, so they flourish. They did extremely well, right? So that reveals the 2 groupings. So sometimes this can tell us more about this grouping, right? So by construction, the whole real life rules that govern this course, everything was okay, right? Because students are free to register. But after the first test, it reviews this distribution. It shows that something more is happening underneath, right? Just some students are ill prepared for this. So we can think of reaction. Maybe we can say, well, so okay, so be it. Or we can say, let's put a prerequisite in the course and say that you need to have at least one scored at least a B plus and above in statistics before you can join this course, right? Something like that. Uh, Not so much as to eliminate them, but to warn them, right? That hey, you know what? We have data to show that if you're not prepared, then you'll be in the first hill rather than the second mountain, right? Yeah. So this can happen, or a test moderate in difficulty, right? And given to students, and because again, you can most of you can understand what is an elective course, right? So the students will elect themselves to register for this course rather than being told that you have to attend. Now, those are the core classes, right? So if they elect, and in a bigger social setting, is like in the society, right, in the country, working adults are encouraged to sign up for classes, right? Maybe if those are evening classes, or if you're doing a evening degree, university degree, then the students, the attendees will come from all walks of life at different ages. So again, you can see this, right? So evening adult classes who study, right, to get a degree, they are subject to the same level of difficulty as full-time students, so no compromise in the integrity of the test. There will be some who are really strong-willed, right? Really strong-willed. They sign up, they pay the school fees themselves, so they really make sure they are falling asleep, they will pull their eyelids and continue to study. Then there is a bunch, right, who try to, but they lack motivation halfway, or things change, or whatever it is, they struggle to continue, right? So also can happen. In a more extreme form, we have lots of failure and lots of you know successful students. So leading to this kind of U-shaped curve. U-shaped curve, of course, has a cliff downwards here, maybe a cliff downwards here. You can call it bimodal, but it's also when this gap is wide, then it is U-shaped. So U-shaped or bimodal, the appearance will be not so good for parametric test users. So in other words, you want to be careful. Okay. Another example is Poisson distribution. So number of, I want to say occurrences, but more concrete example might be daily emergency visits. That means it is count over time. Anything that is count per unit time will be more or less modeled by Poisson distribution, discrete events, right? So these are discrete events. They are count over time, and there is no decimal places, so to speak. It's not like height and weight. It is number of visit. Either you visit or you don't visit. So the visit is either 0 or 1 or 2 in a day. And even if you say, when the clock strikes midnight, my one leg is crossing the room and the other leg is not, you have to exercise a discipline to say, okay, then in that case, you're not in. So long as you're not fully in, you're not in. You're not counted as a visit. One leg in is not counted. Okay, so it's always going to be an integer, full integer, no rounding, no decimal place, right? So these events, not just limited to emergency room visits in hospital, in whatever it is, right, or even in the school, not just for those settings, can be 999 calls, right, in a day, right? Call for help in a day, SOS hotline for emergency family help in a day, and so on, right? So all these are calls. So for Poisson distribution, it is 0 call, 1 call, 2 call, and so on. And can it be infinity? Potentially yes. Potentially yes, like that, and then it tapers down very rapidly, and then there's a long tail behind. it doesn't go to zero. It just so vertical scale is real number. So it can keep crawling slowly to zero, never quite touching zero until infinity. That's the Poisson scale. All right. So of course the y-axis here, they are all relative frequencies. So just so you understand, they are histograms, right? Distributions. Okay. So that's I hope sufficient categories of examples, very different from each other, to enlighten you on these potential measurements. Okay. Next, and the last one, I want to talk about the unequal variance, right? Unequal variance. Unequal variance situations, or heteroscedastic situation. Scedasticity, meaning unequal variance, or change, or differing variances. So recall that in the parametric hypothesis test for two populations, right? So we, in one particular branch or situation, we have small sample size. So we have to either assume equal variance of the two populations, or else use the Welch-Satterthwaite formula to adjust the degree of freedom, pretending as if we didn't have as many sample size. We have even lower sample size. So whatever it is, that was the assumption of equal variance. But in real life, we typically will have unequal variance, or we will lack the ability to just wave our hands and say, let's just assume equal variance and carry on as if nothing happens. Not so likely to happen. All right. So what are the situations? Let's just say, example, student scores. Okay, this could be A-level performance, O-level performance, primary school performances, right? Student scores across districts. Why? Well, because there are rich districts, there are poor districts, right? And how does that translate? I think some of you can guess, right? So the rich districts, we cannot prove it, but socially we can expect richer districts to have more money is one, but resources in general, maybe chauffeur, driver, right, to ferry them back and forth to school and to tuition centers and to piano lessons and to swimming lessons, meeting more people, meeting more professionals, right? So special training, Olympiad training, international competition training, and so on, right? So the richer districts tend to have the ability to give more quality, I would say, right? More quality opportunities to their children, to the students, therefore achieving on average higher scores. Of course, you can always quote me counter examples. Not all rich parents will do that. Yeah, true, right? We're talking about statistically, one can expect that to be so. Okay, and also, in a very interesting way, we will expect the rich and the poor to have different ability to support the students. But we are talking about unequal variance, right? So the rich will tend to reduce the variance in score because they have more but not infinite resources, right? But fixed maximum score marks. So they have a lot of resources. They can push and push, but student only has 24 hours if the students don't sleep. And no matter how powerful, how good, how well they train themselves, they cannot score beyond 100 marks. So there's no way to go beyond that. And so if all the rich students do well, train well, study hard, they will all bunch up themselves towards an average of 99 or even 100, right? So that's it. That's the maximum they can go. So the variance around a high mean performance. So the average could be 92, but they are all centered around 92. So 92 to 99, 50% of people, 85 to 92, another 50% of people. That's it, right? So all the rich get, and the variance very, very small. The gap very, very small. But the poor will have 0 to 100 marks to show themselves, right? So there are those who are hardworking. You don't need to be exposed to all the opportunities and all that in order to do well. You can score well, but not knowing much also possible, right? Because exam, after all, is just this artificial behavior to solve those problems. And all of you know that there are exam tricks, right? Spotting questions and all that stuff. So if one is lucky, one can actually end up on the high side, right? High side of the scale, and some might be on the lower side, some will be mediocre. So the variance, I hope you can see why the variance will be larger, right? More varied settings and environments to cope, right? So higher variance. Okay, then we can talk about property prices. So property prices grouped by, let's say, neighborhood. In all the cities, whether it's Tokyo, Los Angeles, Singapore, in all the cities, there are sectors or neighborhoods, let's call it, that are well known to be lush and luxurious in name and real situation. If you actually visit the area, Ginza area, Denenchofu area in Tokyo, one walk around that vicinity, you already smell the high prices floating around. So one walk around Orchard Road condominiums in Singapore, you will again, sense somewhat of the affordability issue there, right? That kind of settings. So in those areas, the high property price neighborhood, right? How high is high? How high is high? Well, kind of sky's the limit. Right? Recently, I was looking around the property prices in Singapore, landed property prices. Landed property in Singapore is like the premium properties. So unlike big countries, right? In US, almost everything is landed. you own the land and the sky, right? Everything. In Singapore, the landed properties, land is a premium, so landed properties are one category higher price than other housing types. But even in landed properties, there are the cheaper ones. Cheaper ones maybe because they're a little bit smaller. They are in a cheaper neighborhood. They are of a limited lease, and so on and so forth. So various characteristics of the landed property gives them a lower price. The higher range, their sizes, their land is 5 times, 10 times larger. They are situated in a well-known high-priced neighborhood. They have various good amenities around, even though it's their large land and well secluded. But just walking outside that neighborhood, you get good amenities. That's good enough. So on and so forth. So the range can be very varied, as in how high is high prices can be infinity, right? So example, one good class bungalow in Singapore can be offering to be sold at more than $100 million. One unit, one house, right? One house. So one house can be $100 million. Another landed property would be offering a sort of asking price of $2.5 million. Okay. So by property type, landed properties in Singapore, in this city, by the property type itself, grouped by this, there is huge variation in the prices. So that's why the uh, public housing. So public housing prices, like example HDB, right? We will say like smaller variance compared to landed private properties. There will be sky's the limit, right? So therefore, high variance. Known to have higher variance because the control is really by market reaction, right? But the control for public housing better be controlled, or else affordability might be an issue, right? So there is active control to make sure variance is not going to be too high, higher than the private property. Then there's a problem. So kind of like by management, by active management, uh, public housing variance, housing price variance cannot be larger than private property housing variance because it just doesn't make proper social logic to let that happen. Okay, so that's again, we can see that if we are performing price equality comparisons and then assuming equal variance, we'll run into big trouble. Okay, one last example, very easily from the stock market, stock returns, right? Grouped by market capitalization. So large market cap tends to be big MNCs and well-established companies. So we can say that large cap blue chip, right? So blue chip MNCs, they tend to have a more stable price because to move them, they are large capitalization. Meaning what? You want to move the price, you better also have a big pocket, right? Like billions of dollars of money, just to move the price, right? Like just to make the price go up, down, to have high variance. Very difficult, right? So lower variance, relative variance compared to the small cap stocks. Small cap stocks, their overall worth can be like 10 million, let's say. So if it's 10 million, then the deep pocket funds with $1 billion in their hands to manage can easily swing the small caps up and down, right? I can buy out the whole company even. It's just 10 million. I have 10 billion on hand, 1 billion on hand, right? So so in that case, they tend to be having higher variance, relative variance in price. And small cap stocks, because of the fluctuating, changing nature of the price, tend to attract punters, right? Those who are trying to not invest, but more like gambling, right? You're like, I buy, okay, hoping that it will rise today. I don't have the money, but I will just throw in $10,000. I only have $100 in my pocket. I throw in $10,000. I buy, some shares in the small cap. At the end of the day, I hope it goes up by 3%. Then I sell. Oh, I pocket some $1,000, something like that. So, of course, that's a fat hope. Sometimes you win, but most of the times because of high variance, you also can end up hoping that it increases by 5 cents, end up it drops by another 7 cents, right? So, high volatility. Okay, so when it attracts punters because of high volatility, the attraction of punters themselves make the price even more volatile, don't you think? Right, because more punters arrive and they all have different, objectives in mind. Some want to sell short, some want to see the price fall, some want to see the price go up and up. So, and of course that itself, the fact that small cap itself attracts punters. Punters make it more volatile. More volatility in prices attract more punters. So you can see the spiraling effect. Huh? Okay, anyway, I have run out of space and I better stop my video. But I hope through this, no doubt, general discussion about non-parametric test, you will see the potential pitfall, right? And therefore the potential benefits that you can get by using non-parametric methods. So always remember that there are these very good advantages that will help in the integrity of your statistical argument. So when you know that the methodology you use comes with all these very attractive characteristics, you speak and present with confidence. And when you can do that and project that air to your audience, and sometimes very important audience like your boss, your customers, the board of directors, then you get what you want, right? So, and that's much more than just solving problems and getting the calculations right. Okay, that's all for today's video. In subsequent videos, we'll visit the more detailed and in-depth discussions of one population median, two population medians, three population medians tests in a non-parametric sense. Thank you very much. See you then. Bye.